This conference will now be recorded.
Hello everyone. Today we'll start with oxidation states of nitrogen, and after that we will see how the compounds of group 15 reacts with hydrogen and oxygen and also some related problems. Here we have different compounds of nitrogen, and in each of these compounds we will see that different oxidation states of nitrogen are possible. So first there will be some oxides of nitrogen, and after that there will be some other compounds, that is compounds with even hydrogen. The first oxidation state example we will see now is +5, and the example is nitrate ion, NO3 minus. Now how we will be able to understand what is the oxidation state of nitrogen? Here though it is written +5, but how to understand that? NO3 minus. So suppose the oxidation state is X, so it will be X plus. For each oxygen it is -2, and there are total 3 oxygen, so -2 into 3, and this will be equal to the overall charge, which is -1. So the value of X is 6 minus 1, that is +5. So in this way we can calculate for each compound. Not necessarily it is compound, it may be ion also. For example, nitrate is ion because it is carrying one negative charge. So nitrate ion, it is oxidizing agent in acidic solution because their oxidation state of nitrogen is +5, which is maximum oxidation state. Okay, so that is why it will be oxidizing in nature, because it will have a tendency to accept electrons from other species. That is why it is oxidizing in nature. The next molecule is NO2. Now it is neutral. NO2, nitrogen dioxide. This is a gas usually produced by the reaction of concentrated HNO3 with different metals. And the dimeric form of NO2 is N2O4. Now here total number of oxygen is 2. Each oxygen -2 charge. That means 2 oxygen, it must be total 4 negative charge. So the oxidation state of nitrogen, it will be +4, because overall the molecule is neutral, so total positive charge will be +4. The next species is NO2 minus. Now NO3 minus is nitrate, but NO2 minus is nitrite ion. Okay, so try to understand the difference. The spelling is different. Nitrite, here oxidation state is +3. It is nitrite ion in basic solution and nitrous acid in acidic solution. That means if we just add one hydrogen, it will be HNO2, which is known as nitrous acid. So if you keep this ion NO2 minus in acidic solution, it will take proton and it will be converted to HNO2. Similarly, if you put HNO2 in basic solution, now there will be removal of this H and generation of NO2 minus. So that is why it is written nitrite ion in basic solution, nitrous acid in acidic solution. It can be either an oxidizing agent to usually produce nitric oxide gas. It can also behave as reducing agent to form the nitrate ion. That means when it is acting as oxidizing agent, that means it will accept electron, then it is converted to NO. That means conversion of oxidation state from +3 to +2. Similarly, if it is acting as reducing agent, now it will lose electron and it will be converted to +5 oxidation state. So this is reduction and this is oxidation. Both are possible. Why it is so? Because this oxidation state is in intermediate range. It is not very high like +5, it is not very low like +2. As it is intermediate between these two, so that is why it can act both as reducing agent as well as oxidizing agent. And the next species, that is NO, nitrogen oxide or nitric oxide. This is colorless gas produced by the reaction of metals with dilute nitric acid. So metals, when react with concentrated nitric acid, there is production of NO2. And when it is reacting with dilute nitric acid, there is production of nitric oxide. And NO, if it is treated with oxygen, it will be converted to the another oxide, which is NO2. Here one thing is also mentioned, that oxidation state which is in this range, that is +1, it may be +2, +3, +4, etc. All these oxidation states, there is a tendency for disproportionation. Now what is disproportionation? Disproportionation means oxidation as well as reduction both are going on the same species. So HNO2 here oxidation state is +3 because it is nothing but nitrate ion, and it is simultaneously converted to HNO3, that means nitrate ion +5. So it has lost electron. So here it is acting as reducing agent. See, here I have written R. That means from +3 to +5, it is itself acting as reducing agent. But the process is not reduction. The process is oxidation because it has lost electron. But when it is acting as oxidizing agent, that means now it has gained electron, and in that case, now it is converted to NO because here oxidation state is +2. So here it is oxidation and this is reduction because it has gained electron. But remember, the molecule itself is acting as oxidizing agent, but the process is reduction. So is there any doubt up to this? Next we will see some more oxidation state. Next oxidation state after +2 that is possible is +1, and the example is N2O, dinitrogen oxide. It is also called nitrous oxide or laughing gas. Now zero oxidation state you can find in nitrogen molecule itself. It is present in air around 80% and very unreactive. Okay, because of the very strong triple bond. We know that between two nitrogen atom in nitrogen molecule there are 3 bonds. Okay, and this because of this bond, this molecule is very inert in nature, because if you want this molecule to take part in reaction, in that case you have to break all these 3 bonds, which is really difficult process. So that is the reason this molecule is so unreactive. Next oxidation state is -1. Okay, NH2OH. This molecule is known as hydroxylamine. It has very weak basicity property. It can act as oxidizing agent and also reducing agent. Now NH2OH, it is as if NH2 plus HO minus. Okay, in that way we can consider it. Now if we how to calculate oxidation state, suppose it is X. Okay, and total 3 hydrogen, that means 3 positive charge, and for 1 oxygen it will be negative charge. So overall here molecule is neutral, so we will write 0 here, and X will be equal to 2 minus 3, that means -1. So in this way you can calculate the oxidation state of nitrogen, which is -1. The next molecule is N2H4, which is known as hydrazine. This is colorless liquid. It is also weakly basic in nature. Important application is it is used as rocket fuel, and there is a tendency for disproportionation, and after disproportion it is converted to nitrogen. That means from -2 oxidation state it can be converted to 0 oxidation state, that is in case of nitrogen, and it can also be converted to -3. -3 means NH3, ammonia. Here oxidation state of nitrogen is -3. So both are going on simultaneously, that is why it is disproportionate. Okay, so -2 when it has lost electron, now the oxidation state is converted to 0, and when it has gained 1 more electron it will be converted to -3. The next species oxidation state -3, In basic solution, it can exist because NH3 is basic in nature. So if you put it in basic solution, there will be no reaction. But if you put NH3 in acidic solution, it will take proton because it is basic in nature, and it will be converted to NH4 plus ion, which is known as ammonium ion. Not generally used as reducing agent in aqueous solution. It is when burned in presence of oxygen, it is oxidized to either nitrogen or nitric oxide. Okay, and the oxidation of ammonium salt. Ammonium salt means, suppose NH4Cl. So this is ammonium salt. So if we do oxidation, it will produce nitrogen gas. So see, in this table, you can find different oxidation state of nitrogen that are possible, and starting from +5, +4, then 0, and after that there is some negative oxidation state. So the range is starting from +5 up to -3. So see how versatile the oxidation states possible for nitrogen. Okay, is there any doubt? Should I repeat? Anomalous properties of nitrogen. Now, this is not just for nitrogen. You will see that for any group, the first member means the member which is from second period. So for group 15, it is nitrogen. If you consider group 16, it will be oxygen. So the first member always behaves differently compared to the other members. Okay, and why it is so? There are some common reasons for that we have already mentioned before starting group 50. But now we will see individually what are the anomalous properties for the first member. And the first member for group 15 is nitrogen. So this is the general observation that first element of any group will be having some different properties compared to the other elements. The exceptional properties of nitrogen, it is because of its small size, high ionization enthalpy, high electronegativity, and non-availability of d orbitals. Okay, so that is the see, the reasons are small size, ionization enthalpy maximum, because we know down the group ionization enthalpy decreases, and electronegativity obviously maximum, because again down the group metallic nature increases, that means electronegativity will decrease. And there is no d orbital because it is from second period, and in second period there is no d orbital. So because of these specific reasons, it will have some properties which are different. It has a unique ability to form pi-pi multiple bond with itself and some other elements, and these other elements must be small in size and electronegativity should be high. Now, pi-pi bond with itself means, very good example is NN triple bond. So here we have one sigma bond but two pi bond. So pi bond, that is two nitrogen atom, there will be two p orbital and there will be sidewise overlap. And sidewise overlap, if we consider, it is always better between two 2p orbital compared to between 2p 3p or 3p 3p, because when size is increasing, charge is now diffused, so there will be less effective overlap. So that is the reason, if the element which is forming pi bond, if it is from second period, that means obviously it will use 2p orbital because 3p is not possible. And when it is using 2p orbital, the pi bond, that is sidewise overlap, that overlap will be highly effective. That is the reason pi bond is formation is very common. And we have also seen that nitrogen can form pi bond even with oxygen, right? And also with carbon. Now carbon, oxygen, these two are also from second period. So obviously when we are talking about pi bond, carbon and oxygen, these two also use 2p orbital only. But if we consider heavier elements, that is phosphorus, arsenic, antimony, they will not form p-pi bonds because their atomic orbitals are large and diffuse, and effective overlapping now not possible. And the last element of this group, which is bismuth, it is metallic in nature because we know down the group metallic nature increases. So when you have reached at the last element bismuth, obviously the metallic character is maximum. And metallic character maximum means it will form metallic bond. Metallic bond formation is possible only in case of metals, not in case of non-metals or metalloids. So bismuth, as it is metal, so it can form metallic bond. So in this way, nitrogen will behave differently compared to the other members. So see here we have the structure of nitrogen molecule. Okay, nitrogen has 5 valence electrons because it is 2s2, 2p3. Now out of these 5 valence electron, 3 will be used for bond formation and 2 electrons are not used, so this will be lone pair. Okay, so it exists as diatomic molecule with a triple bond between the 2 atoms, and see the bond enthalpy value is very high, and that is the reason this molecule is so unreactive. Because if we want nitrogen to take part in reaction, we have to break all these 3 bonds, which is really difficult and highly energy requiring process, which is clear from this value 941.4 kilojoule per mole. It is really very high value. So see, nitrogen can exist as diatomic gaseous molecule, but this type of bond we do not see in case of phosphorus or arsenic. Just for example, if you consider phosphorus, there is no such molecule. It is not possible. Okay, that means it is behaving differently. That is nitrogen, the first member is behaving differently. It is existing as diatomic and gaseous. But if you consider the next members, phosphorus, arsenic, antimony, they are not diatomic, they are not gaseous. So here we have phosphorus, arsenic, antimony. See, all are tetraatomic molecules. That is, all these are basically phosphorus. This is arsenic. That means they are not diatomic, they are tetraatomic. Okay. So they form single bond. There is no multiple bond, because whenever multiple bond formation is there, that means it has to undergo pp bond formation. But for heavier elements, pp bonds are not so effective. Okay, that is the reason they are forming single bonds only. See, all these are single bonds. So these are the difference, or better we say some anomalous properties of nitrogen, which are not observed in case of the other elements. Okay, any doubt? Should I repeat once more? Now, based on these anomalous properties of nitrogen, we will discuss 2 problems. The first problem is nitric acid is formulated as HNO3, but phosphoric acid as H3PO4. HNO3, this is the formula for nitric acid. But why not the formula is like this? That is H3NO4. This type of formula does not exist. And if you consider phosphorus, the acid having structure like this, it does not exist like HNO3, that is HPO3. Though this type of molecule you can exhibit, but H3PO3 it is more common. Okay, but why it is not existing? That is what is the reason behind that? That we have to understand. So nitric acid, it has structure like this. See, it is basically having that is coordination. If we consider, it is 3 coordination. Okay, and if we consider H3PO4, now see, it is tetra coordination, and there is also a pi bond formation. Now why the structures are different? Now the same reason, because nitrogen will always behave differently. So the reasons that are here important is because of absence of d orbital, it cannot expand its valency from 3 to 5. Okay, and another reason is small size of nitrogen. So higher coordination, that will be very difficult. See here, coordination 5 4, here it is 3. So higher coordination will be difficult. So that is the reason the formula is like this. Okay, N plus O minus. But for H3PO3, here we have 1 PO double bond and 3 OH bond attached to OH group attached to phosphorus. Okay, and if you look at the structure of nitric acid carefully, nitrogen has 5 valence electrons, right? Now it will use 2 electrons for bond formation with oxygen. The third electron it will use for bond formation with this oxygen atom. And this bond is basically coordinate bond. Coordinate bond, sometimes it is also written in this way with the arrow. Now the reason is coordination bonds mean here both the electrons that are present in this bond, both are donated by nitrogen. So if it is normal covalent bond, suppose there is bond between nitrogen and oxygen, one electron is given by nitrogen, another electron given by oxygen. So this type of bond we will call covalent, because each atom is giving one electron. After that there is proper sharing of electron. But instead of this, suppose both the electrons are given by nitrogen, and after that it is just like covalent bond. So this type of bond we will call coordinate bond. Try to understand the difference. Here both are given by one atom only, and that is the reason nitrogen here is carrying positive charge and oxygen is carrying negative charge. So is it clear what is the difference between coordinate bond and covalent bond? So this is coordinate bond. Okay, and as nitrogen has already given its 2 electrons, so that is the reason it is carrying positive charge. Next question is NMe3, which is derivative of ammonia. Just replace all the hydrogens with 3 methyl groups. Now it will be NMe3, that is trimethylamine. It is a strictly Lewis base. Lewis base means the molecule which has the capacity to donate lone pair of electrons. And similarly, if we call Lewis acid the compound which is capable to accept lone pair of electron from some other species, that will be called Lewis acid. Trimethylamine is strictly Lewis base. That means it can only donate electron. It cannot act as Lewis acid. But if you consider the other members, phosphorus, arsenic, antimony, same type of compound, that is trimethyl phosphorus, trimethyl arsenic, trimethyl antimony, these 3 compounds, they can behave as Lewis acid as well as Lewis base. That means they can donate electron as well as they can accept electron. But why their behavior is this difference is there, that we have to see. NMe3, obviously it will behave as Lewis base, because in NMe3 there is lone pair over nitrogen and that can be donated to some other species. But in case of nitrogen, there is no vacant d orbital. As there is no vacant d orbital, how it can accept electron pair from some other species? But in case of these 3 species, vacant d orbital exists. So that is the reason they can act as Lewis acid also. So this is the reason, no d orbital. But in case of these 3 molecules, they will also behave as Lewis acid, particularly in presence of transition metal ions. Don't think that they will they will show Lewis acid with just any Lewis basis. No, it is not that. They will be behaving as Lewis acid also, only in presence of some transition metal ions. Okay, where excess d electrons are present. For example, nickel 2 plus, Pd 2 plus, platinum 2 plus. So see, this is the metal, that is metal means nickel, palladium, platinum in +2 oxidation state, which is having electron in T2G orbital, and these electrons can be donated to this phosphorus. This phosphorus, this is d orbital, but see, this is vacant d orbital, and there is sidewise overlap between two d orbitals, so that is why it is dd pi bond. But see, now metal is donating electron. First, what happens? Phosphorus, it will donate electron to metal. So phosphorus here acting as ligand, that is phosphorus, trimethyl phosphorus. I am writing here 3-methyl group, not just methyl group, it may be any other alkyl group also. So first it is behaving as ligand because it is donating electron towards the vacant orbital of metal, and after that metal is giving electron density towards vacant d orbital of phosphorus, and this type of bond is also known as back bonding. Why it is back bonding? Because first phosphorus is donating electron through sigma bond, and after that there is pi bond formation and metal is donating electron. So as it is occurring after this first donation from phosphorus, so that is why it is called back bonding. So the conclusion is these three molecules, they can behave, they can have dual role, that is Lewis acid, Lewis base, it can act as both, but NMe3 it is not possible. Okay, both the questions clear? Now we will see how it reacts with hydrogen. That means reactivity towards hydrogen. Every element of this group, that is group 15, forms EH3 type of hydride. EH3 means 3 hydrogen atoms attached to E, and here E is basically nitrogen, phosphorus, arsenic, antimony, bismuth. Okay. Now we will compare their hydrides, that is NH3, PH3, ASH3, etc. The first is basic strength. Basic strength down the group decreases. So see, ammonia will be having maximum basic strength, then PH3, ASH3, SBH3, BiH3. Now why it is so? As the size of central atom increases, we know as we are moving down from nitrogen to phosphorus to arsenic, size is increasing. When size is increasing, electron density will decrease. Electron density means what? The total number here, when we are talking about basic strength, it is basically this lone pair donation tendency. Now this lone pair, it is same for all, that is all are carrying one lone pair. That means number of electrons same, but size is increasing. That means volume is increasing. So charge density, it is just like density. What we know, density is mass by volume, right? So when we are talking about charge density, it will be charge by volume. Now charge is fixed because it is one lone pair for each atom, but V is increasing. So the denominator is increasing. That means charge density will decrease, and when charge density will decrease, basic strength will also decrease. So this is the reason that down the group basicity decreases. Okay, this is very important observation. Second is thermal stability. As the size of central atom increases, its tendency to form stable MH bond, basically it is EH. It actually same thing, but as we have here mentioned E, so better we say EH bond. Size of central atom increases. So see, when it is EH bond, H is fixed. But as you are changing from N to P to arsenic, basically the size of E is increasing. So when size of E is very high, what will happen? The distance between E and H, that will increase. That means bond distance will increase. And bond distance increase means you can easily break this bond. And when you can easily break this bond, that means thermal stability is very poor. That is just providing very low temperature. You can break this EH bond. Okay. So when you are reaching BiH3, that is maximum size of bismuth, then thermal stability is minimum. So down the group also thermal stability decreases. Third one is reducing character. Now reducing character means how easily it can donate H. Now in the second point, what we have seen, thermal stability is minimum in case of BiH3. It means what? When it is BiH3, you can easily get hydrogen because BiH bond we can easily break. Now easily get hydrogen means it will show maximum reducing character. So that is the reason down the group reducing character increases. It is maximum. Okay. So it is directly related to the stability. As the stability of hydrides decreases, reducing character increases. And melting point, boiling point, see, it is actually gradual increase, because we know when we move down the group, molar mass increases, van der Waals interaction increases, MPBV both increases. But here NH3, its position should be here, but now it is intermediate between arsenic and antimony. And why it is so? Because as the size increases, this reason I have already said. But why there is exception for ammonia? It is because nitrogen can form hydrogen bonding, which is not possible for the other elements in this group. And that is the reason to break these hydrogen bonds, we have to provide extra energy. So though on the basis of only this statement, the actual order should be like this, that is first ammonia, then pH3, then SH3, but actually it is not. Why? Because the exception is there and the reason is hydrogen bond. Here we have some values of the EH bond. See, these are the hydrides and EH bond dissociation enthalpy in kilojoule per mole. The values are given. The last one, it is highly thermally unstable. And here we have some names also. This is called ammonia, this is phosphine, arsine, stibine, and bismuthine. So see, this type of hydrogen bonding is present between two nitrogen molecule. So this is one NH3 molecule, this is one ammonia molecule, this is another ammonia molecule, and this lone pair of nitrogen, it is donated to this hydrogen, and this hydrogen is coming from another ammonia molecule. So to break all these hydrogen bond, we have to provide some extra energy. That is the reason. So all the